Hypothalamus artificial intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents his products and experiences in the oil and gas sector. This video is confidential and may not circulate outside the receiving company without HI's authorization. This video is confidential and may not circulate outside the receiving company without HI's authorization. Artificial hypothalamus. The power of today's technology is not in the mathematical calculations that it allows to perform, it is in the mathematical calculations that we can imagine that we can perform. Oil supply chain optimization. Oil enterprise-wide optimization integrates mathematical models for each of the links in the oil supply chain, in such a way to management the planning of the supply chain with a holistic vision. The design of HI Oil AWO was the result of work done for a multi-business oil company. The union of models, and their coordination, forms the hypothalamus of an oil enterprise. The current computational power allows to model detailed the supply chain, considering individually all the systems that compose it. This allows to visualize all the existing bottlenecks, and that affect the maximization of economic gains. When all the models that make up a company are solved using the concepts of real-time distributed optimization, an artificial hypothalamus is obtained. Large-scale optimization and artificial brains. One of the fundamental ideas of the artificial brain is the atomization of the system, bottom-up approach, to integrate multiple mathematical models, using the framework of large-scale optimization methodologies, like multi-level Bender's theory, and Lagrangian relaxation. HI Oil meets all the software solutions developed by HI, in different areas of application of mathematical optimization models, oriented to planning and to scheduling operations, in different business of the petroleum product supply chain. All models may be part of the hypothalamus of an oil organization. All models that integrate an artificial hypothalamus must share a general data model in such a way that they are easily integrated. In 2010, HI executed the project The Hypothalamus of an Oil Organization. Challenge: design and implementation of a DSS decision support system. For the optimization of energy resource that links all stream of the supply chain petroleum products, with emphasis on the consumption and marketing of the energy used by the network. Solution: design and prototype implementation of the DSS that following models. Production of crude oil. Transportation of crude oil. Oil and biomass refining. Production and industrial services, and transport of refined products. Result: the model is the base to the formal implementation of the value chain model for a Latam petroleum company. The models were delivered in prototype version, in the sense that the oil company did not have the database in the expected time. This is one of the most important projects developed by HI. Oil production optimization. Oil fields production optimization. Model. Challenge: to implement model to optimize the production process in onshore oil fields, including industrial services plants. Solution: design and implementation of an optimization model that considers the following aspects: the production system, the behavior of the reservoir, the modes of well operation and the energy consumption, and the flow in the hydraulic system. It allows to plan operations in an oil production system that integrates multiple fields, that in turn integrate multiple oil and/or gas deposits, that are exploited through a network of interconnected wells. The interconnection, which occurs in surface facilities and in the underground reservoir, allows gas and oil to be sent using a pipeline transport system, to storages and production facilities for subsequent clearance. A reservoir is a porous and permeable underground formation, containing an individual deposit of hydrocarbons confined by impermeable rock, or by water barriers, and is characterized by a unique natural pressure system. The conceptualization of the field can be done based on the following principles. Well, it corresponds to the basic unit of production. Reservoir, it corresponds to a set of wells that operate an oil deposit that is interconnected in the subsoil, and field, it corresponds to a set of multiple oil deposits which contribute their production to a collection and processing infrastructure. The collection infrastructure is composed of separator, production unit in which oil, gas and water are separated, collector, it is composed of a network of pipes that connect the fields with the separator, and tanks, storages of oil, gas and water, already processed. The topologies of the network can be very varied, since an O&G production facility can have multiple components of each type. Result, a prototype model that optimizes the oil and gas production process including industrial services plants. It is part of the hypothalamus-owned project. Project, Exploration and Production in Investment Petroleum Portfolio Optimization. Challenge, to optimize the portfolio of investment projects in oil exploration and production, (INP), activities. Solution, design a DSS to solve the problem based on non-anticipatory stochastic optimization models, as an alternative to traditional simulation models, whose results should be the effective allocation of scarce resources such as capital, equipment, time, and human professionals. The oil company must face at least two risks: geological risk associated with the possibilities of finding and extracting oil and the costs associated with such operation, and market risk associated with two risks: price risk and volumetric risk represented in the economic revenue that oil can produce. Result, the design was presented to Latam Oil Company as part of a proof of concept conducted in 2017. Project, Oil Fields and Smart Grids Optimization. Challenge, to develop a model for redesign the energy supply system of oil onshore fields. Solution, design and implementation of a stochastic optimization model that includes aggregated simulation of oil field operations, and design of the topology and capacities of the smart grid to supply electricity to support operations. Result, deliver the models to the client, a consulting company, who implemented the models for its end-user client, a Latam Oil Company. Oil refining optimization. Sales and operations planning. Linear model. Challenge, to implement a model to optimize sales and operations planning for refineries and biorefineries. Solution, design and implementation of an S&OP optimization model for aggregated planning of crude oil and biomass refining. Aggregation is associated with process nonlinearities, but not with the level of detail to represent process connectivity. The objective of optimization is to determine the production plan that meets the demand for refined products, according to a supply of available crudes purchased during the planning period. It considers two types of process units. Rigid, a process based on certain inputs, crude, intermediate refined products, that produces refined products in fixed proportions, and flexible considers multiple input mixes in which the inputs proportions and the quantities produced are determined, blended, by the model. Rigid unit, considers a unit as a process that is defined based on certain input, raw material, refined final or intermediate products, and that produces refined products in fixed proportions, and flexible unit, considers multiple possibilities for production processes in which the proportions of the blending of the products consumed, and the quantities produced, are determined by the model. For flexible units, quality specifications must be introduced as part of the model constraints, so that the volume and/or weight product generated by the model meets these specifications. Result, a prototype model that optimizes the oil and biomass refining process at tactical level. It is part of the owned hypothalamus. Refined petroleum production and energy services planning model. Challenge, to develop an integrated production and industrial services optimization considering that the optimal management of power of industrial systems implies a holistic position oriented to integrate the production planning of goods with industrial, energy, services that are consumed in the production plant, and finally integrate it with possibilities of self-production and negotiation of this energy in the energy markets. Solution, design and implementation of an optimization model that simulate the production process, and simulate industrial services process, like boilers, pumps, turbines, electricity plants, collector, compressors, etc. The approach considers that industrial processes have variable speed, and that the power consumption as a function of the speed is nonlinear, it is exponential. Service plant, place where various industrial operations, related to the auxiliary services demanded, by process plants are developed. Auxiliary service, essential services for the operation of any production system. They allow to guarantee the quality and the continuity of the process, and service unit, facilities that make up the service plant. Its function transform the different services to adapt them to the requirements of demand for auxiliary services of the process plant. The main objective is to optimize the management of service plants by considering the fluctuation of demand over time. The optimization of the two plants is carried out in an integrated model. Result: a prototype model that optimizes the oil refining process, including industrial services plants at tactical level. A similar model implemented for the Petrobras Recap refinery, São Paulo, Brazil, achieved up to 10% cost reduction. It is part of the oil and gas artificial hypothalamus. Oil transport, trading and blending optimization corresponds to a dynamic model that optimizes oil distribution between fields, refineries and ports, the oil mix for use in refineries, the mixture of oil for export in accordance with quality standards and established supply contracts, import of oil according to offers in the spot global oil market, and import/export of oil according to offers in the oil derivatives financial instruments. It can be coupled to the production of oil fields, in such a way as to establish optimal plans for production, distribution, export and import. In addition, blending processes extend to petroleum products, for example, lubricants. In the petroleum chain, the blending process of materials takes place in several parts. In the refineries, at the entrance of the refining process, blended crude oil is required, and at the exit, it is necessary to mix the refined products. These blending systems can be located in a distributed manner, which can lead to significant cost savings, due to the flexibility of the crude oil chain. The diagram presents the flow of materials in the petroleum system. The entities considered in the modeling are crude oil, oil field, oil terminal, tank, refinery, oil port, commercial oil, market, and regional market. RAN+I project, oil blending and transport planning and scheduling model. Challenge: to implement an oil blending dynamic optimization model. Solution: design and implementation of an oil blending dynamic mathematical model. Result: implementation of a prototype model in a joint effort with Deloitte Mexico to perform a proof of concept for a potential client. Unfortunately, the customer didn't buy. Pipeline systems optimization. High oil includes solutions aimed at planning and scheduling operations in the supply chain of transportation services. It considers two types of transport: pipelines, and multimodal vehicles, such as tankers, barges, boats, and trains. The models developed by High are tactical pipeline planning, scheduling pipeline batches, real-time pipeline dispatch, coordination of petroleum vessels and installations, and petroleum and refined products distribution. Project: real-time optimization of the operations in oil pipeline systems. Challenge: to design and implement models for real-time optimization of the operations in oil pipeline systems. Solution: design and implementation of a set of optimization mathematical models that include the use of pumping stations and the simulation of operating conditions based on detailed models of the hydraulic behavior of the system components. The solution includes large-scale optimization methodologies. Result: real-time operations model to dispatch the batches of products, heavy crude oil, in the pipelines. In test case runs, it was verified that the difference between minimizing energy consumption and minimizing the total cost of operation can be of the order of 20%. The Oil Express pipeline is composed of two pumping stations and a maritime terminal, FSO terminal. The crude oil is stored in tanks and then transported by the submarine pipeline to the floating oil storage unit for the loading of the tankers. PSO2 pumping station in charge of giving more pressure to the 20,000 barrels oil that are received per hour from the PSO1 station and that are sent to the FSO maritime terminal. PSO1 pumping station receives crude oil from the fields located near to the station and from other oil pipeline. From this station, the crude for domestic consumption is driven to an oil express refinery and to exportation using the FSO maritime terminal. The image presents the profile of the Oil Express pipeline. Comparing the results of the objective function of the two operating policies, it can be observed. The minimum energy policy generates 16.21% of overcost, and the minimum cost policy generates 19.43% of overconsumption. As you can see, the differences are not negligible, and are a measure of the precision that mathematical models can provide when solving real-life problems. Estimating this difference based on good practices and/or mental models is practically impossible. Project, Pipelines Planning and Scheduling. In 2003, HI received a request from a Latam oil company. Challenge, to upgrade the mathematical model to planning the pipeline system, to transport oil and refined products. Solution, design of an optimization mathematical model that determines the sequence, and the volume, of refined products to meet the levels of safety inventory at the terminals that supply the retail market. The model considered constraints in the sequence between the tenders. Result, deliver the algebraic formulation of the models to the client based in continuous time modeling, and large-scale optimization methodologies. Vessel scheduling optimization supports the programming of collection, and/or distribution, operations of products via maritime ways, in tankers and barges. It considers restrictions for delivery and load time windows, distribution of capacities on ship, loading and unloading capacity at the docks, draft capacity of the spring, speed of movement of ships, tanker weight to draft ratio, and synchronization of filling, or emptying, of storage tanks. Research and Development Project, Oil Transport by Sea, Planning and Scheduling. Challenge, to develop and implemented a model that supports the programming of collection and distribution operations of products, oil, coal, using different transport maritime modes, like tankers, barges, etc. Solution, design and implementation of an optimization model for scheduling collection, and/or distribution of products using different transport maritime modes. The transport network considers the following characteristics. Short and medium-term demand. Production planning and process plants. Procurement plans. Storage capacities in the terminals. Minimum inventory and average inventory policies. Carrying capacity and number of holds per type of transport. Port draft. Tidal variations. Draft of vessels according to the loaded weight. Distance of travel between 2 points in the network. Speed of vessels. Energy transportation consumption as a function of speed and load, and cost of fuel. A real case of distribution of petroleum products by sea, with tidal restrictions, is the one that occurs in the planning of the distribution of products from the Talara refinery along the oil terminals in the Peruvian coast. When it is necessary to make decisions about the displacement of the vessel, it is of fundamental importance the correct modeling of the consumption of energy, which has a nonlinear behavior, with respect to the engine speed of the vessel. This constraint can be included in the mathematical model, as well as the modeling of tidal movements when entering or leaving ports. Result, implementation of the model using as a study case the oil products distribution between ports and refineries in the Peruvian coast. The distribution chain of petroleum products. Gasoline distribution optimization model. Challenge, to implement mathematical models for urban routing operations for a consulting company. Solution, design and implementation of routing models for refined petroleum products trucks, in urban and rural areas. Include service time window for each client. Limited number of loading shelves in cargo compartments, inventory levels in tanks, and preparation time for changeover in loaded product. Result, initially, the optimization model handles 250 average daily orders, 169 customers or nodes, 139 trucks, 7 loading docks, 3 shifts. Project, Distribution Planning and Propane Gas Gathering. Challenge, to implement mathematical models for distribution planning and propane gas gathering. Solution, design and implementation of a mathematical model for distribution planning and propane gas gathering. It is aimed at supporting the weekly and daily programming and operational rescheduling of trucks dispatch. The modeling hypotheses are as follows. Fleet of vehicles consisting of multiple type of trucks and multiple type of LPG trailers. Trucks can be moved with or without trailers. A truck can tow some type of LPG trailer. LPG trailers can be dispatched with or without charge. Vehicles move between nodes, or terminals. In the nodes there may be demands that must be met or purchases that enter LPG into the system, and LPG storage tanks may exist in the nodes. Result, the models were delivered to the client. Natural gas systems and markets optimization. HI has developed the HI gas model that can be integrated with high power, to simulate the gas market and the electricity market simultaneously. Applications made with HI gas are described. HI gas describes the process of supply and demand of natural gas. From this point of view, its integration with the electricity system determines the economic equilibrium electricity-gas markets. The entities of the natural gas system are: node, connect the gas system installations; production fields; consumption zones, discriminated by sector, example, refineries, heavy industries, residential, vehicular, and commercial thermoelectric power plants; transport systems, pipelines, and multimodal transport systems using vehicles, pumping stations, compress the gas to transport it, and ports, receive and ship liquefied natural gas, LNG, and have gas storage capacity. Connectivity between the electricity and gas sectors occurs through the demand for natural gas for use in thermal plants, and the substitution of the demand that can occur between gas and electricity. Project, strategic planning for the exploitation of natural gas fields. At the end of the last decade of the last century, Oil Express, a global natural gas company that operated several natural gas producing fields in multiple countries, asked HI for support to define a natural gas field exploitation planning strategy, using highly complex mathematical models, to analyze the entire decision-making environment. The challenge was to develop a model that supported the decision-making regarding the exploitation of natural gas field and its impact on Oil Express finances. Solution: design and implementation of a DSS for management of natural gas oil field strategic decisions like the exploitation period. The models included in the DSS were: electricity and gas economic dispatch simulation, optimization of the gas trading decisions, optimization of the financial and fiscal decisions, and financial simulation of the gas buyers. The analysis was carried out using take-or-pay contracts as a basis. The take-or-pay (TOP) is a contractual clause, requiring the buyer to take the delivery of a specific amount of goods or services from the seller or pay a fine if they do not. Thus, it protects the seller against potential losses if the buyer refuses to complete the purchase by a particular date. A top clause is common in energy industries, including oil, natural gas, mineral, and coal, seeking significant investment. It is also called the kill clause. The contract is normally signed before the companies start oil, natural gas, minerals, or coal exploration. Therefore, it is a type of offtake agreement. Result: the SHTG model, hydrothermal and gas system, the first version of the actual high-power model. Based on the high power, Oil Express makes its decisions that produced successful results that led to higher profits by delaying the exploitation of the gas field for an economically more convenient time, due to the non-sustainability of the market. Successful decisions. For its part, Oil Express has proven that there are no market conditions, that is, do not exist a good set profitable thermal generators that can pay for gas through TOPS contracts, required to guarantee the extraction of natural gas. If it is a question of compensating the situation based on price, if Oil Express sells natural gas at high prices, it is possible that Oil Express must recover bankrupt industrial company assets. Everything seems to indicate that the optimal decision may be to delay the investment, waiting for a market with better conditions. Use case: surveillance of the electricity and natural gas sector. A supervisor of the electricity and natural gas sectors hired HI to solve the following problem. Challenge: to develop a decision support system, DSS, to surveillance activities for the electricity and natural gas sectors. Solution: design and implementation of the DSS that included the following models: electricity and gas dispatch, competitive electricity market equilibrium, Real dispatch of the interconnected system considering the long-term contracts of purchase-sale of natural gas and electricity, and financial statements of the electricity generators considering the real dispatch. Result: a DSS that integrates the models required by the supervisor, based on high power. Project: Natural gas system and market dispatch model. Challenge: to implement a mathematical model to simulate the transportation, production and consumption of natural gas that describes its processes of supply and demand. Solution: design and implementation of an optimization model that includes the following types of nodes. Production fields. Consumption center, natural gas demand nodes discriminated by demand sector, among which are industrial, vehicular, electricity generation, commercial and residential, and ports, terminals, that can receive, and/or send LNG. It is associated with liquefaction, and/or regasification plants. Result: ModPlan gas, is a long-term stochastic parallel optimization model that simulates the optimal dispatch of LNG systems. ModPlan, power and gas, by law, it is the official model in Peru, for the analysis of the expansion plan of the Zine transmission network. Like Herbert Simon, hypothalamus artificial intelligence believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.